Hey everyone, so in this segment, in this video, we're going to be talking about coffee cup calorimetry, which is section 7.7 of chapter 7. Okay, coffee cup calorimetry is associated with the change in enthalpy, delta H. So let's explore that. So you've definitely did this experiment in lab where you used a coffee cup calorimeter. Okay. What is a coffee cup calorimeter? Well, it literally looks like a coffee cup, right? But you got two styrofoam cups that are nested on top of each other, all right? You have a lid, a glass stir, and a thermometer to track the temperature of basically any reaction or anything that's going on in the calorimeter, in the cup, okay? Remember that in calorimetry, what's the goal? The goal in calorimetry is to track the change in temperature of the surroundings based on what the system did, right? So the system is going to do something to the surroundings that's going to cause a temperature change of the surroundings. Either the surrounding temperature is going to go up or down. And we can quantify the amount of heat that the system either absorbed or released based on the amount of heat that was absorbed and released by the surroundings, right? Remember that anything that happens to the system, any amount of energy that is released to this from the system is gained by the surroundings, or any energy or heat that the system absorbed, the surroundings had to lose an equal amount of that heat, of that energy, right? So whatever happens to the surround system is, opposite that to the surroundings. Remember that delta H is at constant pressure, right? So basically what that means is the reaction that's in this coffee cup is not really sealed. It's, basically exposed to the atmosphere, even though there's a lid on top of it. But, the lid isn't really like all that strong in keeping this all like contained or anything like that, right? It's still kind of open to the atmosphere. This is all happening at constant pressure. So that's how we can measure the delta H of a reaction. A lot more simple of a setup than a bomb calorimeter, right? A bomb calorimeter is way more complicated of a setup. You need a tight sealed container, right? A bomb that they call it, the quote unquote bomb. But in this case, nothing's really all that sealed. Okay. Now, if you're going to calculate the delta H of a reaction, realize that the delta H of a reaction is equal to, remember we saw this earlier, that the delta H of a reaction is equal to the heat Q at constant pressure, so Q subscript P, right? So let's say you're running some solution in this coffee cup calorimeter, right? You put a solution in there and you have something reacting in the solution or something's going on in the solution that's causing a change in temperature of the water that is part of the solution, okay? So for one, you would need to know the mass of the solution. You would need to know the specific heat of the solution, right? That's in the coffee cup. And usually that's considered to be that of water. So you guys know the specific heat capacity of water is 4.18. Usually the solutions are dilute enough where you can just assume that. If they were more concentrated, maybe you wouldn't be able to get away with using the specific heat of water, but in this case, it's assumed that the specific heat capacity of the solution is that of water. And then, of course, you need the change in temperature. So if you have a change in temperature, you know the specific heat capacity, which is usually water, just that of water, and you know the mass of your solution, you can get the heat that was either absorbed or released by the solution. Okay? So let's move forward with this concept of constant pressure calorimetry. As I said earlier, the negative Q of a reaction. So imagine that the reaction is releasing heat to the solution. So the reaction lost heat to the solution. So if it lost heat, there's a negative sign associated with it. Any reaction that loses heat, the solution gained that heat from the reaction, right? So negative Q of a reaction is equal to positive Q of solution. But we can, multiply this entire equation by a negative and get the other result, right? That the Q of a reaction is equal to negative Q of a solution, right? Both of these mean the same thing. We just move the negative over from one place to another. But the concept remains the same, right? That an insulated calorimeter that prevents heat from escaping, we can assume the heat gained by the solution equals that lost by the reaction, or vice versa. And I said this, that because the reaction happens under conditions of constant pressure, open to the atmosphere, the heat of the reaction is equal to the heat at constant pressure, which is, by definition, the heat either absorbed or released at constant pressure is equal to the change in enthalpy, delta H, of the reaction. Now, usually we find delta H of a reaction per mole of a reactant, just like we did earlier where we calculated delta E of a reaction. Remember in the practice problems that when we calculated delta E of a reaction, we calculated it as the amount of heat per mole, right? So it's the same idea where if you're going to calculate delta E in kilojoules per mole or joules per mole, you need to calculate delta H as far as energy per mole, right? Joules or kilojoules, whatever the case may be, per mole. Okay. All right, let's do a practice problem associated with that. So magnesium metal reacts with hydrochloric acid according to the balanced equation. So here's your balanced equation. In an experiment to determine the enthalpy change for this reaction, 0.158 grams of magnesium metal is combined with enough HCl to make a 100 milliliter solution in a coffee cup calorimeter. So just think about this. You have a coffee cup calorimeter, you have a 100 milliliter solution in the coffee cup, and you have 0.158 grams of magnesium in there, okay? Reacting with the HCl. So the HCl is in solution, it's in water. That's basically what they're saying. The HCl is sufficiently concentrated so that magnesium completely reacts. The temperature of the solution rises from 25.6 degrees Celsius to 32.8 degrees Celsius as a result of the reaction. So if the temperature went up, what does that mean? That means that this process is exothermic, isn't it? It released heat to the surrounding water that caused the temperature of the water to rise. Now it says find delta H of the reaction as written. They also said use 1.00 grams per milliliter as the density of the solution. Now, why is that important? Why is the density of the solution important? Because they gave you the solution in milliliters. And you guys know that if you're trying to calculate delta H of a reaction, we're about to use Q equals MC delta T here. M is mass, right? Not volume. And there's no volume in Q equals MC delta T. So we need a mass for the solution. So we need the density to convert milliliters to grams, okay? And they also gave us the specific heat capacity of the solution, which is that of water, right? 4.18 joules per gram times degrees Celsius. Great. So we have all of this information. Let's put the problem together. So we know that the Q of the solution is equal to the mass of the solution times the specific heat of the solution times the delta T. Okay? And they want delta H of the reaction. That's what they want. But we know that the delta H of a reaction is equal to the Q, the heat at constant pressure. And because a coffee cup calorimeter is an apparatus at constant pressure, as we just said earlier, then this is also equal to the Q of the reaction. Okay, right? We talked about all of that. That's what this is right here. So this is also equal to the negative Q of the solution. Didn't we say that earlier, that any heat that's being absorbed or released by the reaction is the same amount of heat that's either absorbed or released by the solution, right? Just negative, right? We talked about this. So Q reaction equals negative Q solution. That's what we got over here. Okay, but right now we don't need to worry about the sign just yet. Why don't we just solve for Q solution and then we could put a negative in front of there later. So we need the mass. The mass right now we don't have, but they basically said you have 100 milliliters of solution. And the density of the solution is 1, so that's really easy. For every 1 milliliter, we have 1.00 grams of the solution. SOLN for solution. So we got 100 grams. Okay? And notice there's 3 significant figures there, right? So let's just put 100 grams of solution as our mass. Specific heat, they just told us, is that of water, 4.18 joules per gram times degrees Celsius. Change in temperature is 32.8 minus 25.6. So far looking pretty good, right? Nothing too crazy. Q solution is equal to, let's see, we got 3.0 times 10 to the 3 joules. And you're probably wondering why that's 2 significant figures. That's because when you subtract the temperatures, you get 2 sig figs. So this ends up being, I think it's 7.2 degrees Celsius. So that has 2 sig figs. This has 3, this has 3. So the least amount is 2. So that's why our answer is in 2. Okay. But remember that Q solution is equal to negative Q of the reaction. Right? So we need to basically say that the Q of the reaction, negative Q of reaction, is equal to 3.0 times 10 to the 3 joules, right? If Q solution equals negative Q reaction, these should be the same. And they are. But we don't want a negative term there, right? Let's move the negative over. Q reaction is equal to negative 3.0 times 10 to the 3. And this makes sense, right? That it's negative because this reaction is releasing heat to the surrounding water solution, right? And it's an exothermic process. So the reaction is releasing 3.0 10 to the 3 joules of energy. But we're not done because right now we need delta H of the reaction. That's what they wanted, right? And they wanted it in moles. Actually, the problem doesn't even say it wants it in joules per mole, but we should describe it in joules per mole. Just like we said that delta E is also in joules per mole or kilojoules per mole, we could do it either way. Delta H should be also, okay? Now, realize that we've reacted how much magnesium? 0.158. So if I want to get moles, I got to convert grams of magnesium to moles of magnesium, which, whoa, it's not what I wanted to do. If you look at the periodic table, 24.31 grams of magnesium for every 1 mole of magnesium. And whatever that answer ends up being, I don't have that worked out, but you get a certain amount of moles of magnesium. And then you just take the negative 3.0 times 10 to the 3 divided by the amount of moles to get you kilojoules per mole of, joules per mole. So delta H is equal to, delta H of the reaction is now equal to negative 4.6 times 10 to the 5 joules per mole. Right, how did I get this number? I got that number by taking this number, the negative 3.0 times 10 to the 3, and dividing it. I divided that number by the amount of moles of magnesium to get joules per mole. Okay? That's pretty much it, right? We found delta H of the reaction. Of course, I always, recommend that you try a problem on your own, right? I tried a problem where I calculated delta H of the reaction. In your problem set, you will be asked to do this. So this exact problem is going to be on a problem set. What are they asking you here? They're asking you to calculate delta H of the reaction. And what did they give you? They told you had 50 milliliters of silver nitrate, and they combined it with 50 milliliters of HCl, right? Some concentration in a coffee cup calorimeter. And when you mix those two things, the temperature changes from 23.40 to 24.21. Right? Automatically, you're thinking, oh man, I increased the temperature of my surroundings. What does that mean? That means the system, right, the reaction, had to increase the temperature of the solution by releasing heat to the solution, right? So this has to be an exothermic process where the energy is being released by the system to the surroundings, right? To the surrounding solution. Now, you're probably wondering, well, what's my mass in Q equals MC delta T? Well, if you have 50 milliliters of one thing and 50 of the other, you have a total of 100 milliliters of solution. And they said that you're using 1.00 grams per milliliter as your density of the solution. So you can get mass from density. You have the specific heat, which is that of water. You have the delta T. You can calculate your Q. And then from there, you can solve for delta H of your reaction per mole of each of these things. Okay. Now, wait a minute. How do you get the moles? How do you get the moles? Think about it. You have molarity. What is molarity? Molarity is moles per liter, right? So just think about that. If molarity is moles per liter, we've done this before. You can convert from a volume to moles using molarity. Okay, so I'll let you guys do that. I'll have an answer key for that as well. So I think there's one more slide here. Yes. So practice that problem. And this is just kind of a summary slide of calorimetry. So just to recap, bond calorimetry, we looked at a previous video, that occurs at constant volume, and that measures delta E, okay? Coffee cup calorimetry, though, is constant pressure. That occurs at constant pressure, and that measures delta H. Okay, so just be aware of what each one accomplishes here, so that when you look at a problem, you'll know exactly how to solve it. Okay? All right, that should be it. Thanks, guys, and stay tuned for the next video that's going to talk about a little bit more about all this enthalpy stuff. Okay?